In October of 2021, engineers in the Gobi Desert started a nuclear reactor using sand, not metaphorically. The coolant is a fluoride salt, a mineral compound from the same chemical family as the silicates in desert sand, and it ran a chain reaction at over 800 degrees with no enriched uranium and no meltdown pathway. Let me tell you what that means. Every safety system on every nuclear plant you have seen exists because conventional reactors require intervention to prevent catastrophic failure. This one does not. The salt handles it. You heard that right. A reactor that cannot melt down by thermodynamics alone. And that is just the beginning, because passive safety is not the main thing this reactor proved. Hit a like and subscribe so you do not miss the next one. By the end of this video, you will understand exactly why engineers are calling this impossible. For 60 years, the global nuclear industry ran on a single engineering assumption, that the only proven way to generate commercial nuclear power was to stack enriched uranium into solid fuel rods, submerge them in pressurized water, and encase the entire system in reinforced concrete thick enough to survive a direct aircraft impact. That assumption was not born from physics, it was born from a submarine. In 1954, the USS Nautilus became the first nuclear-powered vessel in history, running on a pressurized water reactor designed by Admiral Hyman Rickover and built by Westinghouse. The engineering logic was clean. Pressurized water was dense enough to slow neutrons, abundant enough to be practical, and proven enough to trust with the lives of a crew that could not surface for repairs. It worked. And because it worked, every major nuclear power program that followed copied the same basic architecture. Westinghouse, General Electric, and their European equivalents scaled the submarine reactor into a power plant, and by the 1970s, pressurized water reactors were generating electricity on 4 continents. The IAEA built its safety frameworks around them. Regulatory bodies in the United States, France, Japan, and the United Kingdom wrote licensing processes around them. The entire economics of nuclear power, enrichment infrastructure, fuel fabrication supply chains, waste storage agreements were architected on the assumption that this was simply what a reactor was. Not one option among several. The only option worth building. Here is where the consensus hardened into something that felt permanent. Every time a pressurized water reactor failed, 3 Mile Island in 1979, Chernobyl in '86, Fukushima in 2011, the response was not to question the architecture, it was to add more safety systems on top of it. Emergency core cooling arrays, passive gravity-fed water tanks, hydrogen recombiners. Each addition was an engineering admission that the underlying design required active intervention to stay safe. Each addition also added cost, complexity, and years to every new construction project on Earth. By 2010, a new nuclear plant in the United States averaged over $10 billion. In Europe, it was higher. Most people never think about this. The light water reactor did not win because it was the best physics available. It won because it was the first physics that worked at scale, and 60 years of regulatory and financial infrastructure had since calcified on top of it like sediment over bedrock. But the wall had a crack in it, and that crack had been sitting in a filing cabinet at Oak Ridge National Laboratory since 1969. In 1965, a team of engineers at Oak Ridge National Laboratory in Tennessee switched on a reactor that broke almost every rule the pressurized water establishment had written. They called it the Molten Salt Reactor Experiment. The fuel was uranium fluoride dissolved directly into a liquid fluoride salt coolant. One fluid, one circuit. And it operated at atmospheric pressure, which meant no pressurized vessel, no catastrophic pressure-driven failure mode, and no requirement for the massive containment structures that made conventional plants so expensive. The MSRE ran for 4 years without a meltdown, without a runaway reaction, and without a single safety event requiring emergency intervention. Most people who describe molten salt reactors as unproven have never read the final Oak Ridge report. The experiment worked. In 1969, the Nixon administration shut the program down. The official reason was budget consolidation. The operational reality was that the Department of Defense had prioritized the breeder reactor program, which produced plutonium-239, weapons-usable material. Molten salt reactors ran on a fuel cycle that generated no meaningful plutonium. From a weapons program perspective, they were the wrong kind of nuclear. The decision to close Oak Ridge's molten salt work was not an engineering verdict. It was a procurement decision wearing the clothing of fiscal responsibility. The program that had cracked the wall was shelved, and the industry moved on. Then in 2011, the Chinese Academy of Sciences announced a thorium molten salt reactor program with a working reactor as its first milestone. The international engineering community's reaction was measured skepticism. The words most commonly used in Western nuclear trade publications were ambitious and premature. One IAEA reviewer called the timeline optimistic, given unresolved materials challenges. They said the same thing about photovoltaic solar in 2000. The International Energy Agency projected solar would never exceed 1% of global electricity. It now exceeds 5% and is the fastest growing energy source on Earth. We all know how that ended. The Chinese Academy of Sciences committed $2 billion and over 700 researchers to the program and established a dedicated facility in Gansu Province at the edge of the Gobi Desert. They had identified the precise problem Oak Ridge could not finish solving. Not the reactor concept, not the fuel chemistry, but the vessel material. Fluoride salt at sustained operating temperatures corrodes conventional metal alloys from within. Oak Ridge knew this. What they lacked was the materials science funding to close the gap. The question was never whether molten salt could work. The question was whether anyone would fund the metallurgy it required to last. And what they built to answer that question is where the story really begins. To understand what the Chinese Academy of Sciences actually solved, you need to understand what makes every conventional reactor on Earth structurally vulnerable by design, and why that vulnerability has been accepted as an unavoidable cost for 60 years. Picture a pot of water on a stove with a sealed heating element submerged inside it. The element generates heat. The water carries that heat away. If the water stops moving, then pump failure, burst pipe, power loss, the element keeps generating heat with nowhere for it to go. Temperature climbs. The element fails. Scale that to a uranium fuel rod with a pressurized coolant circuit as the only barrier between a controlled reaction and a runaway one, and the consequences scale with it. This is not a flaw unique to any single reactor. It is the structural consequence of keeping the fuel and the coolant as two separate systems. In every pressurized water reactor ever built, uranium sits in solid zirconium-clad rods and coolant flows around them, adjacent but distinct. The cladding between them prevents fuel failure from becoming coolant contamination. At 3 Mile Island, that cladding failed. At Fukushima, coolant stopped moving when pumps lost grid power. The physics of separation are also the physics of vulnerability. Now here is what makes this genuinely extraordinary. In the MSR LF1 reactor that reached criticality in the Gobi Desert in 2021, the fuel and the coolant are the same fluid. Thorium fluoride is dissolved directly into the molten fluoride salt. There is no cladding to fail. There is no separation to breach. And because the fuel is dissolved in the coolant rather than suspended inside it, the reactor inherits a property that pressurized water systems can only approximate with expensive engineered add-ons, a strongly negative temperature coefficient. When the salt gets too hot, it expands. When it expands, the fissile material concentration per unit volume drops. When that concentration drops, the chain reaction slows. The reactor cools itself without a single valve turned or pump activated. This is not a safety system, it is thermodynamics. Chinese Academy of Sciences operational data confirmed this during 2023 MSR LF1 testing. The reactor demonstrated automatic load following, adjusting power output in response to external demand changes without any operator input. That is not a safer reactor. That is a different category of reactor entirely, but the liquid fuel that eliminates the meltdown problem creates a different problem, one no reactor in history had been forced to solve at operational scale. And that problem is where the story gets considerably harder to believe. Here is the problem nobody covers when molten salt reactors come up in mainstream reporting. The same property that makes liquid fuel elegant, everything dissolved in one fluid, means the waste products of fission are also dissolved in that same fluid. In a solid fuel reactor, byproducts stay locked inside the fuel rod. You shut down on a scheduled cycle, remove the rods, and ship them to a reprocessing facility. The waste and the fuel are physically separate from the moment fission begins. In a liquid fuel reactor, they are not. The waste is in the coolant. The coolant is the fuel, and one specific fission byproduct will poison the reaction entirely if left to accumulate. Xenon-135 is a gas. It forms during fission as a decay product of iodine-135, and it is among the most powerful neutron absorbers in nuclear physics, capturing neutrons that would otherwise sustain the chain reaction and removing them from the system. In a solid fuel reactor, xenon-135 accumulates inside the rod and is managed through control rods and scheduled shutdowns. In a liquid fuel reactor, it accumulates in the salt itself. Left unaddressed, it starves the reaction from within. The same way fine sediment building in a fuel line will eventually cut an engine off from the flow it needs. Think of it like a coffee press where the grounds dissolve into the liquid instead of staying in the filter. The longer the reaction runs, the more concentrated the byproducts become, and the more they choke the process generating the heat. You need to filter the salt, but you cannot stop the reactor to do it, because stopping the salt flow stops the cooling of the fuel dissolved within it. It sounds like it should not work. That is exactly why it does. The solution implemented in TMSR-LF1 is called online fuel reprocessing. A side stream of salt is continuously diverted through an off-gas handling system, a cold finger mechanism that drops the side stream temperature enough to precipitate gaseous fission products, including xenon-135, out of the fluid in real time while the main reactor loop keeps running. Extracted gases are captured. Clean salt returns to the loop. The reaction continues without interruption. During 2023 testing, TMSR-LF1 achieved 168 continuous operating hours with the online reprocessing system running simultaneously, confirmed by Chinese Academy of Sciences published data. The waste comes out while the reactor runs. The reaction never stops. Running both systems in a controlled test is one challenge. Running them together continuously in a desert facility across months of operation that required a control architecture no molten salt program had ever attempted before. The number most analysts miss entirely is this one. TMSR-LF1 contains over 1,000 individual sensors, not monitoring the building around it, not tracking external conditions, monitoring the reactor itself, salt temperature at dozens of points along the loop, neutron flux density across the core, fission gas concentration in the off-gas stream, thermal gradients in the vessel walls, salt chemistry in real time. In a conventional pressurized water reactor, operating parameters are relatively stable between refueling cycles. Fuel sits in fixed rods, coolant flows at a controlled rate, and operators manage three primary variables: temperature, pressure, and control rod position. The system is complex, but its complexity is bounded. You can predict with reasonable accuracy what it will do next. In TMSR-LF1, every variable is dynamic and coupled to every other. Salt chemistry shifts as fission products accumulate and are removed. Neutron flux distribution changes as fuel concentration in the salt evolves. Thermal gradients across the vessel wall fluctuate as the reactor adjusts its own output. Each of those variables feeds back into all the others simultaneously, and all of them affect the structural integrity of the Hastelloy and alloy vessel containing the entire system. Think of it like conducting an orchestra, where every musician is also retuning their instrument in real time, and the key, tempo, and score are changing simultaneously. A human operator reading gauges cannot respond fast enough. The system has to read itself. The Chinese Academy of Sciences built a distributed control system specifically for TMSR-LF1, integrating the sensor array into a real-time process model trained on Oak Ridge MSRE historical data and live readings from TMSR-LF1's own operational runs. The system predicts salt chemistry drift before it crosses a control threshold, pre-adjusts the off-gas extraction rate, and modulates neutron flux in response, all without operator input. This is not industrial automation in any conventional sense. It is a reactor that builds a continuous model of its own internal state and governs its own behavior from that model. The operational result is an uptime figure that the light water industry has not yet fully processed. TMSR-LF1 achieved over 300 operational days in its first full year of testing. The global average for conventional light water reactors per EIAEA Power Reactor Information System data is approximately 260 days. That is not a marginal availability gain. That is a structural shift in what a nuclear facility can deliver per year of operation. When the verification results from that first year came back, the number required a second look before anyone would put their name on the publication. Here is the honest picture. TMSR-LF1 is a 2 megawatt thermal research reactor. It is not a power plant. The jump to the minimum 100 megawatts thermal required for commercial viability is not a linear engineering problem. It is a materials durability challenge of a completely different order. The Hastelloy N-alloy variants developed for TMSR LF1 have been tested for years under operational conditions. A commercial reactor needs them to perform for 4 decades. That gap is real. Anyone who tells you otherwise has not read the materials literature carefully enough. Now here is what the verified data from TMSR LF1 actually shows, with that caveat on the table. Thorium fuel utilization reached 60%, confirmed by the Chinese Academy of Sciences in a 2023 publication in the journal Energy. In a conventional light water uranium reactor, less than 1% of the fuel loaded into the core is actually consumed by fission. The remainder exits as long-lived radioactive waste, spent rods cooled in pools, transferred to dry cask storage, eventually destined for a geological repository engineered to remain intact for 10,000 years. Read that again slowly. Less than 1% utilized, against 60%. That is not an efficiency gain. That is a different fuel cycle. The plain English translation is this: the thorium needed to power a city of 1 million people for a year fits inside a single standard shipping container. The equivalent uranium load, accounting for enrichment and the fraction actually burned, would fill a warehouse. And most of what filled that warehouse would emerge as waste requiring isolation longer than human civilization has existed. If that number surprised you, the next part is going to be even harder to believe. Hit subscribe so you are there when we cover it. The waste profile compounds the utilization figure because 60% of the thorium is consumed rather than less than 1% of uranium. The volume of long-lived waste produced is a fraction of the conventional figure. Remaining fission products require isolation for approximately 300 years, not 10,000. The part nobody covers is what that difference means for the back end of the nuclear fuel cycle. The part that has made waste a generational political problem in every country that has tried to site a permanent repository. 300 years is within the planning horizon of modern engineering. 10,000 is not. The thorium decay chain produces no weapons-usable plutonium-239 in meaningful quantities. That is not a political statement. It is chemistry. That is not a cleaner reactor. That is a reactor that redefines what the nuclear waste problem actually is. The global nuclear industry has been contracting for 30 years. Not because the physics stopped working, because the economics did. The Vodal Units 3 and 4 in Georgia, the most recent American nuclear project to reach completion, came in at approximately $35 billion, more than twice the original estimate, and required 16 years to build. The Flamanville EPR in France entered construction in 2007 at a projected cost of 3.3 billion euros. It achieved first criticality in 2024 at roughly 13.7 billion euros. Hinkley Point C in the United Kingdom is currently tracking toward 35 billion pounds. Here's what most people get wrong about why nuclear became unaffordable. The answer is not public opposition. The answer is the architecture. Every major cost driver in a pressurized water reactor program traces to the physical consequences of running fission inside a pressurized vessel. The vessel requires specialized steel forgings manufactured by only a handful of facilities worldwide. The containment dome must withstand a full coolant loss pressure event. The emergency core cooling network multiplies in complexity with every regulatory update. A molten salt reactor at atmospheric pressure needs none of those systems. No pressurized vessel. No emergency core cooling. The containment footprint shrinks accordingly. The International Energy Agency's 2023 Nuclear Power and Secure Energy Transitions Report acknowledged advanced reactor design, including molten salt variants, as credible net zero contributors for the first time, citing their potential to reduce the capital cost structure that has made nuclear uncompetitive in liberalized electricity markets. The affected sectors extend beyond electricity. Molten salt reactors operate at temperatures sufficient for industrial process heat. The heat required for steel, cement, and chemical production. These industries account for roughly 20% of global carbon emissions and have no proven low-carbon heat source at the required scale. The historical parallel holds. Combined cycle gas turbines were technically proven by the early 1980s, but regulatory frameworks written for conventional gas plants delayed wide adoption by nearly a decade across OECD nations. The IEA estimated that lag added approximately $30 billion in unnecessary energy costs to member economies. The limiting factor was not the engineering, it was the absence of a template for a fundamentally different machine. Thorium is 4 times more abundant in the Earth's crust than uranium. Dozens of countries with no domestic uranium, India, Brazil, Australia, Norway, hold significant thorium deposits. The limiting factor for global nuclear expansion has never been uranium supply. It has been enrichment infrastructure. A thorium molten salt reactor removes that dependency at the fuel cycle level. The limit that held for 60 years was technical. It has now been demonstrated as solvable. For 60 years, the question underneath every nuclear energy debate was never really about safety or waste or cost in isolation. It was about whether the architecture the industry locked itself into in the 1950s was the only architecture that could work, or whether it was simply the first one that did, and the weight of everything built on top of it had made every alternative look impossible by comparison. That is the question TMSR LF1 was actually built to answer. It does not answer it completely. It answers the part that physics can answer. A reactor running on a compound from the same mineral family as desert sand achieved sustained criticality, demonstrated passive safety without a single active intervention, ran continuous online reprocessing for 168 hours without interruption, utilized 60% of its thorium fuel against the less than 1% a conventional reactor consumes, and produced waste requiring 300 years of isolation instead of 10,000. Those results are verified. They are published. They are not projections or modeling outputs. They are operational measurements from a working reactor. If you made it this far, you now understand more about molten salt reactor technology than most people who write about it for a living. What was actually proven in the Gobi Desert is not that molten salt reactors are ready to replace the global fleet of light water plants. What was proven is that the engineering ceiling the industry accepted as permanent was a ceiling built from the constraints of 1950s, materials science, and 1960s procurement decisions, not from the limits of nuclear physics itself. The physics were never the problem, the Hastelloy was. And for the first time since Oak Ridge shut its doors in 1969, there is now a verified answer to the question of whether those constraints can be overcome. The implication, carried to its logical end, is that the 100+ countries currently priced out of nuclear power by the capital cost of pressurized water reactor construction are not priced out by an immovable physical law. They are priced out by an architecture. And architectures, unlike physics, can change. If this changed how you think about nuclear energy's future, hit that like button and subscribe so you never miss what comes next. Now I want to hear from you in the comments. Do you think molten salt reactors will reach commercial scale within 20 years, or is the gap between a 2 megawatt research reactor and a 100 megawatt commercial plant still too wide to close in that time frame? Both sides of that argument are worth making. Drop your answer below.